In this next question, question number 3, we have transition element. So what's the definition of a transition element? As you know from the syllabus, it forms compounds. It forms compounds where it has, actually it forms compounds or ions where it has incompletely filled d orbital. Incompletely filled d orbitals. So if you have completely filled d orbitals, then it can't be considered a transition element. If you have partially filled d orbital, then it will be transition element. If you have totally 0 electrons in your d orbitals, then it's also not going to be transition element. So you cannot have something which is completely empty in the d orbitals. You cannot have something where the d orbitals are completely filled. Those will not be defined as transition element. Only when you have partially filled or you have incompletely filled d orbitals, then you can call it transition element. I've used this word incompletely filled. If you use the term partially filled, that will be perfectly acceptable as well because they mean the same thing. The next bit, name the type of bonding that occurs between ligand and a transition element. So they will form a complex. If you know how to define what is meant by a complex as the syllabus required, you will know that the name of the bond is called dative covalent bond, where both the electrons in the covalent bond come only from one atom. This one has another name. It is also known as coordinate bonding. I typically stick with this dative covalent bond, but because it's stated in the syllabus that they could use coordinate bonding, so question can describe coordinate bonding, and you will be expected to say that they are the same thing as dative covalent bond and be able to define them the same way. In the following question, which of the following species can act as a ligand? Definition of a ligand. So it have lone pairs. It have lone pairs of what? Lone pairs of electrons. And what does the lone pair of electrons do? They will form dative covalent bond. So they are the one with the electrons, and they will donate both the electrons in the covalent bond. And what do they donate to? They donate it to metal center, which could be atom or ions. Now what we have here is NO3 minus. So can it act as a ligand or not? Complete the table by placing a tick in the appropriate column to indicate whether it can act as a ligand or not. So it's not like a tick or cross, it's just a tick. If it can act as a ligand, put a tick. If it cannot act as a ligand, put a tick here. So you have to have a tick for every single line. That's the thing that's confusing about this question. You do not put a cross because they say put a tick in the appropriate column, whether it can or cannot act as a ligand. Well, let's see about BF3 first. BF3, from your AS case study on shape of molecule, 3 bond pairs. And then you get 0 lone pairs. You have 0 lone pairs of electrons. How can you even act as a ligand when you don't even have the electrons to form the dative covalent bond to begin with? This one is trigonoplanar, 120 degree obviously from your shape of molecule. But there's the very mere idea that it has 0 lone pairs, it cannot act as a ligand obviously. This next one, this is 2 amine there. So this is ethane 1,2 diamine. So this is the common EN ligand. So there's the EN ligand there. It is a bidentate ligand. A bidentate ligand because one molecule of that ligand can form 2 dative covalent bonds, as you have these 1 and 2 lone pair sites that can form 2 dative covalent bonds per single ligand. So it can act as a ligand there. NH4 plus, despite how it looks very much like ammonia, but this is called ammonium. Ammonium is an ion, is also in the AS under dative covalent bond. How does it look like? This is ammonia, trigonal pyramidal with a lone pair 107.5 degree. But then when you pick up another H plus, it's going to go to 109.5 degree tetrahedral, as dative covalent bond is also a sigma covalent bond. So 1, 2, 3, and 4 sigma covalent bonds, and you have 4 bond pair and 0 lone pair. They repel equally the bond pairs, giving you tetrahedral 109.5. Having said that, you will have 0 lone pair, 0 lone pairs. So you already used up your lone pair for picking up a H plus, therefore this thing cannot act as a ligand. Ammonia can act as a ligand because you still have the lone pair. Ammonium cannot act as a ligand because no more lone pair there. How about this NO3 minus? This one looks a bit tricky, but if you know how to draw display formula, when oxygen forms single covalent bond, it has a negative charge, just like hydroxide, right? This is oxygen forming single bond, it has a negative charge. We know it's NO3 minus, I've got -2 there, because nitrogen, when nitrogen form 3 covalent bond, is uncharged. When nitrogen form 1, 2, 3, and 4 covalent bond, it must have a plus charge. Nitrogen here, 1, 2, 3, and 4 covalent bond, it must have a plus charge. This oxygen doesn't have any charge because it formed 2 covalent bonds. This is how the structure of NO3 minus looks like, and you should be able to think of this just like carbonate as well. 120 degree. This is 3 bond pairs and 0 lone pair around nitrogen. In the AS syllabus, candidates should be able to describe the shape of molecules and ions, including ions, analogous. Analogous means similar to whatever is in the syllabus. This is the ones that are in the syllabus. This is similar to the ones that are in the syllabus. You are expected to know the shape as well. So NO3 minus does have lone pair. Where are the lone pair? Not on the nitrogen, but on the oxygen. So there are more than one lone pair there. I've just shown you one lone pair there. The mere fact that you have lone pair, it can act as a ligand. Part C, so the very last bit of this question, this 9-mark question. So we have manganese ions that can show similar chemical properties to those of copper 2. So copper 2 is your case study. As you know, reaction with hydroxide, reaction with ammonia, what else? Reaction with ammonia, hydroxide, and chloride as well. So what we have here is use this information and the data booklet, suggest the formula of the manganese species formed in each of the reactions. When they say the data booklet, they're really talking about reactivity studies, especially for this H2O2, you can get redox reactions. So you have to think about something called E0. So this is E-ox versus E-red, and then you need to think about the overall reactions, which is the E-cell. When you just deal with these OH minus, usually we are talking about precipitation reaction, something that all level, GCSE or IGCSE level student we have heard of, as most metal hydroxides are going to be insoluble. So this is going to be precipitation. As you know, all the transition metals ions, they will precipitate out with hydroxide. This is manganese plus 2. So when they precipitate out, you're going to get Mn, 2 plus, and then OH minus, 2 of them. Precipitation reactions, you are probably expected to be able to write the equation for it as well. So aqueous ions from the sodium hydroxide come together, they give you a solid. This is the classic equation for any sort of precipitation. Balanced atom, balanced charges, show the symbol. Aqueous and aqueous, solution and solution come together to give you a precipitate. And the next one, well, I guess like if they say behave just like copper 2, if you want, you can put down the one with H2 or 4 of them, where you replace 2 water molecule with OH minus and the charge cancel out. So I guess this one, or you can write MnOH twice, this with 2 hydroxide, and H2 or not 6, because you only replace 2 out of the 6 water, so there are 4 water. That should be okay as well, just like copper 2 plus chemistry. With the concentrated HCl, if you have copper 2 plus, you will end up with CuCl4, 2 minus, as that one is plus 2, and you have minus 1, and then you have 4 of that, minus 1 chloride, overall is 2 minus. So what are you going to get here? MnCl4, 2 minus as well. This is just going to be your classic ligand exchange. If you don't like the word ligand exchange, you can probably use the word ligand substitution. So spell that out properly. Ligand substitution, don't have much space here. So I guess ligand exchange, or you can write ligand substitution reaction. The very last thing, I'm pretty sure that there is some sort of redox reactions, but to determine what product you will get eventually, we have to look at the data booklet. Just give me a minute to open up my data booklet. So if you look at H2O2 in the data booklet, of course, in your real paper 4 these days, your new syllabus, your new 2022 exams would be having the data booklet, the E0, whatever values, they'll be provided in the question paper itself. So this is the 2015 paper, so we still have those data booklet as a separate document. So if I look at the H2O2, we can be thinking about this Mn2 plus as manganese plus 2. So do you want to go lower oxidation number or higher oxidation number? If you go lower, the manganese 2 plus will be reduced to manganese metal. That means this one is acting as a reducing agent. If it acts as a reducing agent, it will behave as oxidized reducing agent. Then we're looking at this getting itself oxidized. We're looking for H2O2 on the right side of the E naught equation. So I can find H2O2 in front. That will be plus 1.77 volt, where the H2O2 gets reduced. But to have H2O2 getting oxidized, you have to look for H2O2 on the right hand side. So to have H2O2 on the right hand side, meaning to say the H2O2 act as reducing agent, I do not really see that. I do not really see oh yeah, there is. Okay, so there are two. Let me see if I can find some space there. Let me just move this one up there, I guess. No, that doesn't work. Is this okay? No, that's not okay. Okay, never mind. Let me just remove that equation there. I guess I don't really need that. So let's have a look at some of these redox thing. If I have H2O2 plus 2H plus 2 electrons going to 2H2O, this is plus 1.77 volt. And then I have one where the H2O2 is on the right hand side, O2 plus 2H plus 2 electrons, and again I get H2O2 on the right hand side. This one is plus 0.68 volt. If you look at something that involved the Mn2 plus in the equations, you're looking for Mn2 plus on the right as well as on the left. If I have one where the Mn2 plus is, well, there is a lot of the Mn2 plus on the right hand side. So something, and then Mn2 plus on the right hand side. You can have 3 plus going to 2 plus, which is plus 1.49 volt. You can have MnO4 minus, no, that doesn't. MnO4 minus going to Mn2 plus is plus 1.52 volt. And try to look for Mn2 plus on the left hand side now. If I have Mn2 plus on the left hand side, so what would that be? I'm just saying we are playing around with stuff, right? If I have Mn2 plus on the right hand side, I have plus 1.49 volt, I have plus 1.52 volt from the data booklet, from the data booklet. If I have Mn2 plus on the left hand side, so that will undergo reduction, they will gain electrons, and that will give you the Mn metal. That thing in the data booklet show minus 1.18. Now you got to compare this with these, So if the H2O2 act as oxidizing agent, then this is going to go higher oxidation number. So if this is getting oxidized, we are looking at Mn2 plus on the left hand side, which is this and that. If this act as oxidizing agent, this itself will get reduced. And if this get reduced, we are looking at H2O2 on the left hand side because they undergo reduction. Now this is plus 1.77. Plus 1.77 is bigger. It is more positive than this. If this is your E red, because they undergo reduction, it is more positive than your E ox. So H2O2 will react with Mn2 plus if this act as oxidizing agent because itself will get reduced because this is E red, so it will act as oxidizing agent. Whereas if we look at the other way around, if this act as reducing agent, then this becomes your E red, and this becomes your E ox, where the H2O2 is on the other side, E ox, and this thing, the E red is less positive than this, plus 0.68 volt. This and this is not going to work. H2O2 will not act as reducing agent for Mn2 plus. Cannot reduce Mn2 plus. If you compare this E naught value, this is less positive than that. But it can oxidize Mn2 plus aqueous. What are the possibilities? Both of them are going to be more positive than this H2O2 getting reduced itself. So have a look in the data booklet. You can get the products that contain manganese plus 1.49 volt. That one just now was Mn2 plus on the right hand side, so that is going to Mn3 plus, so you can say Mn3 plus aqueous. Or it could be the one that give you plus 1.52 volt. That was the one that give you MnO4 minus, I guess. Hang on, does that make sense? Because if that is your E red, then that is more positive than your E ox, then it could happen. And if these get oxidized, it could give you this or this. So both of these are acceptable. By using the data booklet, the E naught value, this is probably the hardest one to think about. That is your redox type of reaction there. And that's it really for these 5-mark questions. And this is the end of that 9-mark transition metal question.